Hey, everybody, and we're back. We are now at part 2 of our module 2 demonstration. In part 1, we covered all things ANOVA. We talked about how to run an ANOVA in R, how to visualize it, how to interpret the results, get effect sizes, run post hoc tests, do all that. We also talked about some very useful cleaning and coding techniques, including creating factor versions of variables that are categorical. And we're going to do a little more of that in part 2. So here we are in part 2. I'm down on line 121 of my code, if you want to follow along with me. And we're actually going to shift gears and start talking about multiple linear regression, or MLR, as it sometimes is referred to. And to do that, we're going to use a new data set, which is a longitudinal survey, the NLSW, the National Longitudinal Survey of Women. It is what it sounds like. It's a data set that's been collected for decades now, particularly from just out of women who are just out of high school through the end of their career. And the focus of this was on understanding women's experiences with the job market, thinking about things like equity and pay and so on and so forth. And so it's a good data set to learn regression on, because there are a lot of interesting variables you can use and kind of play with. So this data, again, are in Stata format, and the data set is called NLSW88.dta. And so I'm going to, again, use that same trick I used in part 1, where I import this data set using read_dta. I'm going to call it NLSW88. I'm then going to view it in my window to get a look at it, and I'm going to glimpse it to get a sense of what how the variables are coded and what their structure is, or at least what R thinks the structures are. And so here's the data set. It's a pretty big data set. We've got over 2,000 individuals with a lot of different variables, different demographic variables, as well as information about where they live, what type of job these women have, how long they work, so on and so forth. So there's 17 total variables in this data set. And then looking at the glimpse, ID, age, race, married, never married, grade, college grad, South is whether or not you live in the South. This is a measure of metropolitan statistical area. So it has to do with, I think, like what sort of geographic location you live in, industry, occupation, union, wage, hours, TTL, EXP, and tenure. So a lot of interesting variables here to look at. I think TTL EXP is total experience on the job or something like that. Anyway, so we are going to use the same approach here that we used before, in that we want to create a factor variable that represents a variable that we know is categorical. And in this case, we're going to look at this variable married. So married is what we call a special variable. It's a dummy variable. It only has 2 values, yes or no, whether or not you've been married before. And so this should be categorical. In the data set, you'll notice R recognizes it as a double and attaches a label to it. There's a label that came from Stata, which is just married or not married. But since it's being treated as a double, that's not quite what we want. We want it to be recognized as categorical. And so we're going to use this as factor function to convert this variable married into a categorical variable. And to do that, we'll create a new variable called married.fac. And so same process here. I'm creating a new data set called NLSW.clean. And it's going to start with NLSW. And then there's that pipe operator. I'm going to mutate. I'm going to create a new variable called married.fac, and that is going to be equal to a factor version of the original married variable. And then I'm just going to glimpse it again just to make sure it did what I want it to. So here is my new data set, NLSW.clean. It has 18 variables instead of 17, which is great. And when I look at it down here, here's the new variable. Notice it says single, 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 married. And when I look at the original married variable, it goes 0, 0, 0, 1. So this has taken the labels from the numeric variable and use those as its categorical distinctions. So that's great. That's exactly what I want. I wanted to use those labels. So now I can use this in some modeling. As always, with any good method, visualizing is fun. And so when you're talking about regression, one of the more common ways of visualizing is when you have a continuous predictor and a continuous outcome is a scatter plot, an XY scatter plot with individual dots representing your observations. And so that's what I'll do here. And the command for that, so in ggplot, there's a geom point. So that's a scatter plot, geom point. And the command at the top, again, looks pretty similar. ggplot, here's my data. Notice it's my clean NLSW data set. Here's my mapping. On the x-axis, I'm going to put tenure, which is how long you've been in a job. And on the y-axis, I'm going to put wage, which is essentially hourly wage. So there's a relationship between how long you've worked in a job and how much you work per hour. So that's my XY. Here's the geom point. What's cool here, I think Erica put this in, so you can customize these a little bit. So you can make the points blue by using the color command, and you can change the size. So the larger the number, the bigger the size of the dot, the smaller. I think 0 is the limit. And then we're going to put a title on here, relationship between wage and tenure. X is number of years on the job, Y is hourly wage. And then we're going to give it a nice caption. Always love a good caption in a figure. So the data come from the National Longitudinal Survey of Women in 1988. And here's our N, 2,246. Ta-da! You get a little warning here. This is actually nice to pay attention to. So it says removed 15 rows containing missing values. So that means those are people who are missing either wage or job or tenure. And so if you run a regression, for example, you're going to lose those 15 people as well. We'll talk about later in the course some strategies for handling that, but at least for now, it's something to pay attention to. So here's our relationship. Here's our caption. And it's kind of an interesting relationship, right? So first of all, you have a lot of people up here that don't really know what they're doing, right? We're not sure of what this relationship is. They're people who haven't worked very long, who earn really high wages. But for the most part, we can kind of see a slow positive increase here for years on the job and hourly wages. So it seems to be something of a positive relationship. So to run an actual regression for this, we're going to start with a simple linear regression, what's called a bivariate linear regression. And that is one X and one Y. And I'm going to give this a name. I'm going to call it linear model 1, because I'm going to come back to it later. And the command for regression is really easy. It's LM. And that just stands for linear model. So I'm going to specify a linear model with wage as my outcome and tenure as my predictor. Notice outcome comes first, then this little tilde sign, and then predictor, then a comma, and then you have to tell it where the data are. That's all it is. Very simple. And in fact, when we add predictors, we're just going to add variables with a plus sign like we did with ANOVA. And then we're going to ask for a summary of that linear model 1 to get a little kind of regression looking table that we can interpret. Okay, so here are my results. First thing we get is what's called the call. So that is the actual model that you ran and the code that you specified. Residuals. You can tell R is a stats program because the stat heads and the methodologists are very interested in things like residuals. So for us, we're just sort of most interested in, you want this mean or median value to be close to 0, if at all possible, and hopefully it's pretty symmetric. In this case, it's not terribly symmetric, but when we talk about assumptions later on, we'll talk about tools to help work with that when that assumption of normality of residuals might be violated. And residuals, of course, are just the difference between the observed and the predicted value. I don't need to go into that there. I'll come to it later. I've realized I might go down a rabbit hole. And here are your estimates, your coefficients. First off, we get an intercept. So the intercept is a very important thing to wrap your head around. The intercept is the predicted value of y, your outcome, the predicted value of your outcome when all predictors in your model are equal to 0. Okay, so I'll say it again. The intercept is the predicted value of y when all other predictors are equal to 0. So in this case, it's 6.68. And what that means is for someone in your data set, a woman in this case in your data set who has been on the job for 0 years, 0 tenure, we would predict that she would earn $6.68 an hour in wages. Okay, so the predicted value for someone with 0 years experience is $6.68. And that estimate is statistically significant, which means it's different than 0 in this case, way different than 0. It's very significant. Okay, so that's the baseline. That is the y-intercept. If you're going to draw a line, basically that crosses the y-axis, that's where it's going to cross at 6.68. The line is going to have a slope of 0.19. So what does that mean? Well, in this case, for every 1 unit increase in tenure, we would expect a woman's wages to increase by 19%. This is back in 1988. So for each year, we would expect a 19-cent increase in wages. So if you if you've been on the job 1 year, then you would earn 19 cents more than $6.68. If you work 2 years, it would be 38 cents. If it was 3 years, it'd be about 60 cents, so on and so forth. So that's the model that we've estimated. That's the relationship between years on the job and wages. And again, it is highly statistically significant. So this is similar to ANOVA's. This p-value is in scientific notation, 2 times 10 to the negative 16th. That is teeny tiny. And 3 stars, again, gives us our significance codes. So that is significant. Okay, we get some other sort of model fit related information down here. We get a residual standard error, which is equal to this on this many degrees of freedom. And we get a little message that 15 observations were deleted due to missingness. That's really good to know. Here is our multiple R squared and our adjusted R squared. And then here's our overall F statistic, our test statistic, and here's our p-value. All right, so these are for the model. All this is model fit information. I really like to pay attention to, well, first of all, this thing should be statistically significant. That is the overall test for your entire model. So if you have nothing in your model that is significant, not an intercept or a predictor, then this thing is probably not going to be statistically significant. And that just means you have a crummy model. It's not doing a very good job of predicting your outcome. R squared is very useful in that it represents the percentage or the proportion of the variation in your outcome that you're actually able to explain. So in this case, the multiple R squared and the adjusted R squared are basically the same. When you start to add more predictors, you really want to trust adjusted R squared much more because it accounts for having crummy predictors in your model. But anyway, they're both around 0.03. So that means we're only explaining about 3% of the variation in wages. So tenure on the job only explains about 3% of the variation in wages. It's not a lot. It's not a ton. And I always think it's interesting to know just how much of the variability in an outcome we're able to explain. And we can actually visualize this in our scatter plot with an added regression line. So I'm going to pause here. So this is the sort of basic format for a regression. And then we can make a line. This gets a little bit more complicated because we add what's called a smoother. And that's the command down here. So essentially the top is identical to what we had above. And then we add a smoother. So plus stat smooth. And a smoother is just sort of a line that goes through your data that estimates a little slope each step along the way. And this method is called LOS. We don't have to go into what that's called, but it basically shows you the more or less the relationship between your X and Y variable across the whole range. And we'll make that a red line and make it size 1. So there we go. So this is cool. So it's not we didn't ask for a linear line. And the reason I like to do this is sometimes you can see like some nonlinear stuff in your data, which you can then account for. But we see more or less a straightish line going through the data. We get some curve here. This is some nonlinearity and maybe some nonlinearity here at the end. But yeah, again, more or less, we do see a pretty straight line. And if we were to extend this, it would cross the y-axis, or actually right here, it does cross the y-axis at about 6 or 7, which is actually our intercept up above. So that's a nice way to kind of visualize that relationship. Okay, so that's simple linear regression, 1x, 1y, pretty straightforward. Now, of course, we can add more predictors to this. And this is called multiple linear regression, or MLR. This is, for me, is when regression gets really interesting. It's when we're able to include lots of different variables in the model at the same time. When you just have 1x and 1y, it's honestly not all that different than running a correlation, because you're not controlling for any other variables in the model. You're not accounting for possible confounding variables or things like that. So now we're going to add some predictors. So this is linear model 2. And again, this is going to be, and so it's going to store up here once we run it. And this is a linear model. Wage is the outcome, tenure. And then to that, I'm going to add age, which is how old the person was, grade, which is how far they went in school in terms of years. So grade 12 would mean high school education. Beyond that would be college. 16 would be college degree. And then I'm also going to add that married factor variable that we made at the beginning when we cleaned our data. And then, of course, the data here. And notice the nice part about adding variables, you just add with plus signs, nothing too fancy. And now we've built another linear model. And now we get lots of information. The structure is still the same. Here, interestingly, the intercept is no longer significant, and that's just kind of a function of what you've included in the model. It's just kind of shifted a little bit. It doesn't really have a lot of practical importance. Tenure is still significant. So even after controlling for age, grade, and marriage status, tenure is still a significant predictor of wages, and it's still, about the same. It's 15 cents a year. Your wages go up. That seems really small, doesn't it? Age is sort of borderline significant. It's at the 0.1 level and it's negative. So that would mean that for every year you get older, you actually earn a little less. That's actually doesn't seem good. That's an interesting relationship. But grade is very strongly statistically significant. And one rough rule of thumb that I like to teach, when you look at this, when you look at these t values, so that's just the estimate divided by the standard error. The variable with the highest t-value is usually your strongest, most important predictor. And so in this case, tenure has a value of 7, grade has a value of 15. So years of education is really the strongest predictor, which makes sense, right? With more education, you generally are able to get more high-paying jobs. And that effect is about 0.7. So for each additional year of education, you'd be expected to earn about 70 cents an hour more. And married, so here's married. This is that factor variable. It's negative by about 0.49. Okay, so what does that mean? This part is always tricky. So we're gonna take it just a little bit slower here. So when you incorporate continuous variables into a regression model, their interpretation is pretty easy. A 1 unit change in tenure predicts a 15% or 15 cent change in wages. It goes up, right? And that's true of all continuous relationships. But a factor variable is a categorical variable. It is not continuous. And so this idea of a 1 unit change doesn't make any sense because it's not on a scale. It's just whether you're in one group or another group or another group. And in this case with married, we have two possible categories. So you're either married or not married. And what we have here is the estimate for married. And so what this is saying is for a woman in the data set who is married, they would be predicted to earn on average 49 cents an hour less than someone in the data set who is not. So it's a mean comparison between your two groups. So it's comparing people who are married to those who are not. That is how the inclusion of all categorical variables work pretty much in regression. They always are comparing to what's called the reference category, the category that is not included. So in this case, married is included, which means by definition, not married is not included. So those are the folks you're comparing to. Those folks essentially are living in the intercept, but we'll talk about that. Okay, so that is how you handle categorical variables in regression. Regression is very flexible. It can handle those variables no problem. You just have to keep straight which variables are categorical and which variables are continuous. All right, just a couple other little things. Often it is nice to report what are called standardized coefficients. So if we look up here, back here at our linear model 2, all of these coefficients are slightly different, right? In that tenure is measured in years, age is measured in years on the job, age is measured in years, and grade is measured in grade levels. So there's, those are slightly different. And then we have this variable married, which is also a little bit different too. It's just a comparison. And so it's not really an apples to apples comparison to just look at these coefficients and say which one is bigger. Obviously grade is the biggest one and it has the biggest t-value too, but sometimes it's nicer to report standardized coefficients where everything is standardized according to standard deviation units. So it enables a cleaner comparison. So one option for this is the reg helper package, which again, you'll need to install if you don't have it. And reg helper will convert your model to standard deviation units. And that's what this command does here. So you just do library reg helper. And then I just created a new object called lm2 beta. And that is just equal to the beta function applied to my linear model 2. So I'm just taking the results of linear model 2 and I'm creating standardized coefficients. And then you can just print that out to your console and see it. And so notice these values look a bit different than above. They're all written in scientific notation. So 1.41 times 10 to the negative 1, that's actually 0.1. So the effect for tenure is about 0.1 standard deviation units. The effect for age is about, let's see, 0.03. The effect for grade is about 0.3. And the effect for married is about 0.04. So clearly grade and tenure are the biggies. They're about, they're much larger than the others, but now everything is in standard deviation units, which can be nice. Okay, so I also really like to show you tools for summarizing your model results, because while it's nice to look at the results here in your R Markdown file, it's also really nice to look at them in other places too. So what I recommend is this package called Model Summary. Model Summary is a great way to visualize and also to put results in tables. So the command is library model summary, and you'll need to install it up here in packages if you haven't. And what you do is you first create a list. And a list is just what it sounds like. It's a group of objects that are put together in one spot. And so I'm going to create a list called models, and that is going to summarize the two models I want to put in a table. So I want to put linear model 1 and linear model 2 in a table. And so I put them in a list called models. And look, notice up here in my environment, I now have a thing called models, which is a list, which is great. Okay. And then now that once I have that, I can just say model summary of models, and then output is a default. You can actually change this to Microsoft Word. Excel. It'll pump out these tables for you, save you a ton of time. I highly recommend it. As somebody who spends a lot of time making tables, so much time making tables, it really can help a lot. So you get a nice little formatted table that shows you your results. So I don't know why the text is kind of gray, but you can always copy and paste it into Word and change it to black if you want. So here's your intercept. Here's model 1. Here's the effective tenure. And then in model 2, we added all these other predictors. These, the top line are your estimates, and your standard errors are in parentheses. Plus you get R squared, adjusted R squared. You get AIC and BIC, which we're not going to talk about right now. But these are just like model fit statistics that go with each one. So it's just a really nice way to summarize multiple models at once. And you can also make a plot with this package, which is cool. So once you have that package loaded up, you can do model plot. And I'm just going to plot this last beta coefficient model. Let's see. For models of class summary.lm, the statistic argument of the model must be one of term estimate. Oh yeah, maybe I need to change that to linear model 1 or linear model 2. Let's see if maybe it doesn't like the beta coefficient. That was it. Did not like the beta coefficient. So this is a plot of the coefficient estimates. So here is the x-axis shows you the coefficient estimates, and these are all of the different variables and a 95% confidence interval. So if visualizing this stuff is more your speed, that's a cool way to go too. All right, so lots here in part 2. We talked about all things regression, and we'll spend more time with regression as the weeks go on. So no problem if it seems a little overwhelming. We started with a plot, a scatter plot, which is kind of the basic tool of regression. Then we learned about simple linear regression. Then we added some more predictors. And then we talked about getting standardized coefficients and creating tables and plots based on the results. So that'll hopefully get us started. Have fun, and we'll talk soon.